This is the third video about my autonomous boat project called Gumption Trap. The first two videos dive into all the technical details about how it works and how it was built, some upgrades I made. This one's just going to be demonstrating it operate on probably its most ambitious mission yet. I'm doing about a 2-hour drive across Ladybird Lake in Austin, Texas to plot the depth of the bed as it goes. You can watch the older videos for all the technical details, but the short version is that it's solar powered. It runs on 2 brushless motors in the back, steers with differential thrust, has a sonar module to map the depth, and it navigates based on a GPS and compass signal to follow predetermined waypoints that are stored on an internal SD card. And it also uses that SD card to log all the data as it goes. The only real hardware changes since last time are that I've painted it orange. I put a slightly better camera on the front to get some better onboard video. It's not waterproof, but it's cheap enough that I'm not that concerned about damaging it, and it's powered by this battery pack. Also, I've replaced the propellers with these toroidal ones. I've got another video about how I optimized this propeller design. They are 3D printed. And all this is just a transportation stand I built to strap it down and not worry about it bouncing around in my truck. Other than that, the rest of the hardware is all the same, but I have made some significant improvements to the code, and all this software is open source, and I'll have a link to it posted somewhere. Here I am about to launch the boat. I tend to just plop it in the water from a public boat ramp, but really it can be anywhere. Ideally just somewhere uncovered so it has a GPS signal from the get-go. And unfortunately I couldn't film and put it in the water at the same time, but here it is taking off. This is real-time speed. It's fairly slow, so most of the clips later on are going to be sped up. Just keep that in mind. But next I'll go into the time-lapse from the onboard camera and kind of discuss some background as that plays. This is the time-lapse footage. It's about a 40x speed, so the mission was a little bit under 2 hours, and this is condensed down into a little bit over 2 minutes more or less. And this footage is stabilized in post-editing, so that's why you see it kind of looks like the pontoon on the right is moving in and out there. The camera's actually fixed onto the boat. That's just a consequence of the stabilization. But anyway, so this boat, like I said earlier, it's a dual pontoon setup. The pontoons are made out of PVC pipes. It's got 2 brushless motors, steering with differential thrust, non-reversible ESCs, so it's forward only with the differential thrust. It's powered by a 12-volt solar panel, and that feeds into a 12-volt lithium, or rather lead-acid battery, and that battery's about 2 amp hours. The microcontroller is a Teensy 4.0, which is running my own custom software that I wrote specifically for this. It navigates with a compass and a GPS module following a predetermined set of GPS coordinates. It also has sensors for the battery voltage and the current draw from the panel, as well as the current draw from the motors, so I can see how much power it's producing, how much power it's consuming at the same time. So most of this boat is super low budget stuff. All the electronics are cheap off of eBay and the internet, and a lot of the hardware is just whatever I could find that would work at Home Depot and Walmart, but it gets the job done. The only really expensive part is the Blue Robotics Ping Echo Depth Sounder, which is the sonar module that I'm using to measure the depth as it travels. It's taking it's automatically taking a depth measurement every 30 seconds along the entire mission, so it ends up with quite a few points by the end. You can see me popping in and out of frame there in that red kayak. At one point, kind of towards the end, I pulled some seaweed off of it. Also, kind of a fun fact about this lake, they recently pulled a bunch of dead bodies out of it, right roughly in the area that I was filming in, so that's kind of neat. But here it is pulling into the boat ramp at the end. It was supposed to hit the boat ramp, but wound up in the trees. The rest of this video is just going to be some kind of cool shots of the boat driving around, and I'll mix in some of my data analysis. I've got all kinds of cool plots and charts from the data I recorded, but I know what most of you really want to see is going to be the final depth plot that it produced, so I'll show that up next in just a second here. Another thing to bear in mind as you watch some of these clips is that I'm filming from a moving kayak, which makes it look like the boat is moving in weird directions sometimes. Like it looked like it was going backwards there, but really just my kayak was going forwards. This is a preliminary depth plot I made from the raw data using a MATLAB script. So all of these black dots are individual sonar pings, depth data points, plotted to the latitude and longitude they were measured at. So you can see some kind of cool ridges and features in the path where the boat actually went, but of course all this area out here and out here with no data points where it's just smooth, that's just an approximation. This basically works by just creating a smooth surface, extrapolating and intersecting through all the points. So it's a 3D model I can totally play around with. Really cool plot, and I can flatten it out too. By the way, that beeping you might hear in the background of some of these clips, it's my radio transmitter I've got in the kayak with me. It beeps when it hasn't received any inputs at all after a few minutes, and I'm not actually using it to do anything with the boat. I just have it with me in case I need to take over manual control to steer around a paddleboard or something. But fortunately, I did not need to do that. It stayed in autonomous mode throughout the entire duration of these almost 2 hours during this mission. So the depth scale is in millimeters, and the deepest points it measured, a big cluster of points right here at about 7.5 meters. That's roughly 25 or 30 feet or so. And it seemed to be traveling kind of right along where the deepest part of the lake was, up through where it slopes up to the shore near this side. I should have made it go a little closer to the shore on this side because it didn't really catch any points sloping back up this way, but I was trying to be real conservative with it, not wanting to beach it or crash it into anything. This is definitely the coolest map that I've made with this robot yet. I'd really like to come back and do more missions in the same area, and I can combine all the data together and make a bigger map with a lot more data points. So I did truncate off some of the points at the start because the depth was basically 0 and it threw the scale off all crazy. But it started up here and then zigzagged back and forth across the lake, and then once it got to the end, took a more or less straight line back this way. And you notice this area here where all the points are really close together. So these points are going exactly every 30 seconds. So you can tell it was moving slower there. That's actually where a piece of weed got stuck in the propellers. This upcoming clip has some good footage of it taking a turn, just to give you an idea of what the turning radius is on this boat. It turned out to be better than expected for having a differential thrust steering with the props so close together. The props are 6 inches apart, center to center, and they are shrouded, so when one's not spinning, there is quite a bit of drag from the shroud on that side. Here's the raw GPS data for the path it took, latitude, longitude. Probably isn't to scale, but just wanted to show off the resolution here. So this was a sampling rate of about once per second. So this is the start, plopped it in the water, taking a GPS coordinate about once a second, on to the zigzagging path, and then turning around and coming back at the end. In this plot, I've overlaid the planned coordinate path with the actual measured GPS location. So the blue line is just a straight line as the crow flies between each GPS coordinate. The first one is right here where my cursor is, and the boat actually started out on the shore about over here. So it was supposed to kind of zigzag along just like this. And there's a couple interesting things to point out here. In particular, you can see it well with this leg. So this should have been a roughly straight line from this point to this point, but the boat kind of went for an outwards curve, and then the further along it got, the sharper that slope became back towards the point. So what's actually happening here is there's a strong crosswind coming from this direction. So when it's far away, the wind is slowly blowing it off course, but it's always correcting its course with the compass data. So the more it gets blown off course, like as it gets to over here, it turns back in towards the point. So it kind of started turning left there. As the code is right now, it does not make any correction whatsoever for wind, current, things like that. It just always points itself towards the next point. So that's why we end up with these curves instead of straights. You can see that happen to a lesser degree on just about every one of the straightaways in this direction. And you'll notice the curve kind of goes the opposite way when it's heading back and the wind is coming that time from its right. You'll also notice on the straighter sections like this one, where it's pretty much going straight downwind, it keeps a straight line pretty much perfectly with the plan there. Same thing here and here, because then it's not in a crosswind. And it does have about a 10-meter tolerance for the waypoint distance, so that's why it starts turning before it's actually reached right on top of the waypoint. When it got to this final point, it was supposed to make a straight line all the way back there, but you can see it kind of went crazy and veered off to the right kind of sporadically. And this is around the right time where I pulled a bunch of seaweed off of it, so I think what probably happened is that caused some uneven drag that made it lose its steering authority, and it went all the way over here to where I actually got the seaweed off, and then it corrected and went pretty straight the rest of the way. Here's a side-by-side with the Google Maps screenshot of how I actually picked these points out. I basically just pulled up the satellite image, clicked on the map, and typed the GPS coordinates into my SD card. Over here, this boat ramp is where I actually launched from, and I did end up adding a couple more points after I took this screenshot, so that's why there's some extra over here and up here. Here's that same line kind of poorly transposed onto the actual satellite image. You'll have to bear with me, I'm an engineer, not a photo editor. This is all the depth data overlaid onto the actual satellite image. It's kind of interesting, the lighter, shallower areas line with this little peninsula over here and some of the shallower areas under the bridge. Closer to this shore, it seems a lot deeper and the deepest measured points were out here, right in the middle, towards the wider part of the river. These graphs show the data collected by the power monitoring sensors. This top one is the current draw. So the blue line is the total current draw from the motors and the entire system, and the black line is the current produced by the solar panel, both at 12 volts. So interestingly, the solar panel power is very straight and consistent, and you'll notice it trends linearly downwards as time goes on. That's because later in the day the sun is setting and the incidence angle gets worse and it produces less power. This was filmed and this mission was done from about 5 o'clock to 7 o'clock in the evening, so I'm confident that could have been a lot higher if it was done around solar noon, and I'll definitely aim for that next time. But in this instance, the current draw was more than the current produced, so overall the battery voltage trended downward during the operation. It started at pretty much full in the high 12s, and it ended up in kind of the mid 11s, close to empty. This little temporary dip in the solar panel current output is when a cloud passed in the sun. Kind of interesting that that showed up. But anyway, I used MATLAB to integrate this plot with respect to time, and I found that the total current consumed during the mission was 1.875 amp hours, which is pretty near the nominal capacity 2 amp hours of the battery, and the total produced was 0.57, or about a third of what was consumed. So the battery almost certainly would have died if the solar panel wasn't active. So even if we're still net consuming rather than producing power, the solar panel is still helpful to extend the overall duration of the battery life just by supplementing it a little bit. And I thought I'd add the reason this voltage and the current both are so jumpy everywhere is because the motors are constantly making adjustments and changing speeds. These two plots show the steering data. The top one is the PWM of the port motor in black and the starboard motor in blue, and the bottom one is the compass heading over time in degrees. So the PWM value is essentially the throttle, with 0 being no movement and 1300 being the max I allowed it to go during this run. So these spikes down to 0 are when it makes a sharp turn and it completely turns one of the motors off. You'll notice that always coincides with one of these sudden changes in the compass heading. That's because the compass heading jumps quickly as it makes a sharp turn. Some of these spikes they look a lot bigger than they really are because when it hits 0, it loops back around to 360. So that's what's going on there when it makes turns in the same direction multiple times in a row. And then you'll notice these sections that kind of gradually slope down. That is from, as I discussed earlier, when the wind was blowing it off course, and the heading is just slowly changing as it constantly readjusts to be pointing towards the goal. I wish that I'd also tracked the goal heading on my black box. I don't have real live data from that. It would be interesting to see the actual heading, which is what's shown here as measured on the compass, side by side with the goal heading to see how well it's keeping up with that. But you'll notice in the pulse width modulation, if I zoom into one of these sections, one of these brief straightaways, it'll have one motor pegged at 100%, and it's constantly making very small adjustments with the other one to keep it on target, and it doesn't actually spend very much time with both motors at 100%. The reason it's making all these tiny adjustments so frequently is just because my steering gain wasn't set high enough. And if you look at my error log here, it gave this can't reach target heading a lot throughout the entire trip. That occurs if 10 seconds pass and the actual heading is not within a few degrees of the target heading. So the reason for that is because the steering adjustment is not enough to significantly alter the heading quick enough, and so it doesn't quite reach the point where it keeps both motors at 100% because it's constantly struggling a little bit to reach the target heading. The strong wind was also a reason why those adjustments were made so frequently. Even though the wind doesn't necessarily rotate the boat itself, it translates it relative to its target waypoint, and so the target heading is constantly changing a little bit in the event of a crosswind. The steering setup is not true PID control, it's proportional only. So if it gets to a point where it's struggling to reach the set point, like it did a few times during this mission, it just kind of reaches an equilibrium a few degrees off and is constantly making minor little adjustments but never quite fully reaching the goal. So definitely by the next major mission, I'd also like to add in integral and derivative control. And that, combined with the use of the GPS course, the actual direction of travel, instead of just the direction it's pointed in for some of the calculations, could, I think, really help it with these steering in the high wind conditions. Here's a quick look at the real important part of the autopilot code. I'm not going to go into a ton of detail on this because I have in previous videos, and this will be available for download if you want to take a look. The major change since the last version is I changed a lot of this logic to use discrete PWM signals, whereas before I was kind of controlling it as like a virtual servo in degrees that didn't really make that much intuitive sense. So this A high variable is the maximum allowable PWM speed based on the throttle limiting, and this is basically just linearly mapping the differential thrust based on the difference between the current heading and the goal heading. So that's like a proportional control, and here's where the gain multiplier comes into play. I had that set to 2 for this video. Here's the final clip of the boat nearly missing the boat ramp and beaching itself there in the weeds and the trees. So I'll show a few highlights from the onboard camera, and then I'll just wrap up with some final thoughts and future plans. I didn't notice this until I was editing the end of the video, but you can see there the boat very nearly ran over that little bird chilling in the water. But don't worry, it managed to miss the propellers, thankfully. That was a fish jumping in the water. I was pretty close to it when that happened in real life, and it looked way bigger and way closer than it did on camera. I thought that would be a lot more exciting, but still a cool animal sighting for you. Some final thoughts with this. I do plan to keep going with this setup, doing some minor improvements and tweaks to it as it is, as well as using it as a test bed for improving the code and the PID control in the future. But I do want to iterate it in the physical design with a brand new hull built from scratch. I'd like to ditch these PVC pontoons and replace them with maybe either fiberglass, carbon fiber, something that would give me the same amount of buoyancy with a lot less weight. I could build it up bigger and have room for more solar panels too. That would allow me to take full advantage of the motor power without throttle limiting if I had a higher power budget. I'd like to swap out the ESCs for some better ones that are reversible. That would let me turn in place by running the props in opposite directions. I'd also like to add a rudder. That would just give me a little better drive control overall. And one kind of neat idea that I had was to put a servo on the sonar module that would let it tilt forward slightly, and I could use it to detect the shore as the depth slopes up in front of it. Then I could run it in kind of like a Roomba algorithm to where it just randomly goes in lines until it like hits the shore and then stops and turns around. That way it could run a totally autonomous depth plot by just driving randomly and not requiring any pre-planning on my part at all. But anyway, lots of ideas for this, and I do plan to continue with it. So thanks for watching this video.